Hello everybody, I am back with a new video and I'll be discussing today about Benzyne reactivities in light with molecular orbitals and orbital coefficient and also charge distribution. So let us proceed. As already in my previous videos, I have already discussed how to construct molecular orbitals, how to calculate the charge distribution, uh, orbital coefficient, energy levels, all this. Okay, so please follow those videos for your better understanding. Our main idea to make those videos was to understand the reactions and reaction mechanism, to predict the product and also stereochemistry. So this is one of such problem which I am going to discuss now. Let us start with these questions. Okay, if you take this benzene add phenyl lithium, it can give you meta and ortho product. So which one will be forming preferential? And also, if you take this benzene with the amine, similar way, it can give you these two products. Okay, amine can be either C2 or C3 position. So which one will form preferential or exclusive? Also, while discussing this, I'll be also covering. So if you consider reaction between alkyne and nucleophile, alkene and nucleophile, which one will undergo rapid reaction or faster reaction? Also, if you consider electrophilic attack on alkene or alkyne, which is more feasible? Okay. So, if we before we go in these details about their go to their answer, so I'll be discussing a bit about their orbitals. So, frontier orbitals. If you think about ethylene, it has pi and pi star. So, two pi orbital are parallel, so they can undergo nice overlap. Same way, of course, the sigma bonding is the, I would say, for sigma bonding, the overlap is the most. So, they are most stabilized. Okay, then pi. But compared to ethylene, if you consider the benzene, these two orbitals are bent. So, they are bent apart. They doesn't undergo so nice overlap. Okay, the overlap is poor, which leads to less overlap integral and less stabilization. So because of the stability is less compared to this HOMO, for the benzene this HOMO will be much higher in energy. Okay, and at the same time LUMO will be lower in energy compared to the pi star of the ethylene. These two together, benzene has low lying LUMO, so it can accept electron from nucleophile easily. Okay, so it can act as a nice electrophile. At the same time, benzene also has the HOMO which is higher in energy, so it can also give electron nicely to a electrophile. So it can also act as a nucleophile. Though benzene can act as a both nucleophile and electrophile, it reacts preferentially with the nucleophile. Question is why? How we can explain it? In a similar note, we will be discussing about why alkyne react much readily with nucleophile than alkene, why alkene react much readily with electrophile than alkyne. The answer is here. If we think about benzene reacting with electrophile, what intermediate it will be generating? A sp2 aryl cation. We know this is quite unstable. This is a trigonal phenyl cation, unstable cation and disfavor. So that's the reason benzene doesn't react with electrophile. So it doesn't act as a nucleophile. So it's quite rare. Okay, this is not so feasible. But if you think about the benzene acting as an electrophile, it and reacting with a nucleophile to get this type of aryl anion, this is quite stable. Okay, it's a trigonal phenyl anion, comparatively stable and much favored. Okay, so this is the reason benzene react much readily with nucleophile, not with electrophile. Now, if we think about the alkyl reacting with electrophile, what we get? A alkyl cation. This alkyl cation is much stable cation and more feasible. Okay. At the same time, if you react with a nucleophile to unactivated alkene, okay, which is not that stable because not that feasible because alkene anion is a less stable tetrahedral anion. Of course, for some foreseeing condition we do observe, but this is compared to this cation, this anion is much less feasible. Okay. At the same time, if you think about the alkyne reacting with electrophile, this gives you trigonal vinyl cation, not phenyl, vinyl cation. Okay, and this is also unstable cation, and this type of reaction is disfavor, like benzene case. Of course, it can react with nucleophile easily to give you this type of anion, which is trigonal anion, comparatively stable and much favored. So this type of intermediate is quite common for our retrosynthetic analysis. Okay, like your phenyl anion also we use quite often in our retrosynthetic analysis. Of course, this cation also quite feasible. Okay, we use quite a lot in our retrosynthetic analysis, and we do also observe. Though this type of carbanion is quite, I would say, it is feasible, not as regular as this carbocation, but this one I think is quite less common. Okay, quite we observe this rarely. Okay. Also, if we check the nucleophilicity, the reaction of benzyne with RLI or R this type of sulfide, it quite fast, then amide, then alkoxide. And also iodide undergo faster reaction than bromide, than chloride. Actually, this follow the soft nucleophile react faster with benzyne. Okay, and this this is the more polarizable, and also nucleophile become much harder in this direction. Okay, from here to there, this is more harder nucleophile. Actually, benzyne is a electrophile. It's a soft electrophile. It has a low-lying LUMO and also uncharged. This make benzyne a soft electrophile. Soft electrophile react with more polarizable and soft nucleophile. Now we discuss about this part, this outcome. But if you think about this reaction, the phenyl lithium, okay, it how what is the product outcome? Okay, let us go to the next slide. As already I discussed during our molecular orbitals construction, you can easily see that in the sine curve 180 degree, the middle one is the highest lobe. Okay, you can also calculate their orbital coefficient. I have already discussed, so please follow that video, my first video. So for psi 1, the coefficient at the maximum at the middle. For psi 2, the coefficient is 0 at the middle. Okay, because of this is a symmetrical system. And for the psi 3, the coefficient again is maximum at the middle. And also, if you think of the parallel cation, so because of the that charge distribution, okay, that also prefer the positively charged atom is C1 and C3. Same for carbanium, the negatively charged uh, atom will be C1 and C3. So when cation is get react with a nucleophile, okay, its LUMO will be reacting. Okay, so LUMO will be that these two are the having maximum orbital coefficient. So these two will be reacting easily with the nucleophile should attack to the the parallel cation at the C1 or C3. And also the also it is positively charged, so that will be also coulombically it will be also preferred. Okay, these two are the reason. And at the same time, for your this parallel anion, this is a nucleophile itself. Okay, but let's say another nucleophile attack to this parallel anion. So where it will be reacting? It will be attacking to the LUMO. It will be psi 3. You know the maximum coefficient at the C2, so it should attack at the C2. Not only that, the charge distribution. So these two terminal carbon is negatively charged, obviously. So nucleophile doesn't like a negatively charged center, so it should react at the C2. So if we use this for this benzyne, we can think about this CF bond as a partial carbocation. Okay, this type of vinyl carbocation. Okay, partial. So overall, it will be parallel cation. So parallel cation will be attacked by a nucleophile. Obviously, it will be attacked at the CT. Okay, so it will be reacting here in this terminal, and the negative charge will be coming here. And also this nucleophile, because of this parallel cation, this is also positively charged, these two terminals. So this is positively charged, so coulombically also preferred. Not only that, there is a fluorine atom which has a minus I effect, so that also prefer also stabilizes this carbon intermediate. This is about reaction of phenyl lithium with A. Okay, so this product form as a exclusive. Okay, now if we think about this pyridine and this benzyne, as I discussed earlier. So this is like nitrogen has a lone pair, 2 electron, and this has a 2 electrons. So it is a 4 pi electron system. Okay, parallel anion, right? Okay, and a nucleophile will attack. So it will attack at the psi 3, which is the LUMO for this system. So coefficient maximum at the C2, and also 2. If we this is a calculated charge distribution. So this middle carbon is positively charged, as I also discussed earlier, that two terminal for parallel anion, these this and this has 0.5 0.5 negative charge. So the central one is uh, preferred for the nucleophilic atom. That also preferred here. So the orbital coefficient is maximum, charge distribution also preferred. So altogether, the orbital coefficient, Coulomb, also Coulombic force, and the charge distribution altogether, it react at the C2 position. So we get this as a major product. Okay, and for this case, this. So this is the nice way we can explain using the molecular orbitals theory, frontier molecular orbital theory, I would say. And okay, thank you very much for listening to me. I'll be back with another video soon. Thank you.